Alright, this is section 9.2 notes, so we're going to need your T table this time, not your Z table, because what's going to happen is today we are actually going to test mu when standard deviation is not known. But just a review from the day before, just quickly, if you do know your standard deviation, alright, then you know that it's a normal distribution and you're going to use a Z-score. Just remember that you have to claim those three pieces of information: the null, the alternate, and your alpha, or your magic number, first. And then we're going to find our test statistic, which will be a Z-score. If I know my population standard deviation, compute the p-value, and then you kind of compare. What's different about today? The only thing, honestly, the difference is that your alpha is not known. Okay? So then we're going to instantly jump to a t-score. What's the only difference? You do not have the population standard deviation. You're going to have to use the sample standard deviation, which should be given in your problem. And the only thing that'll be different then is we need the student's t distribution, or your blue sheet, to find your p-value. And this is a little bit tricky, so that's why I want you to grab your blue sheet, and we're going to just dive right into an example. Okay, this is the same process except when you get to finding your p-value. So, input of inflation, basically economists predict that the average cost of a hypothetical food basket in Tennessee in July would be your number right there. And then the standard deviation of a sample of 35 baskets was 950. And then a sample of baskets was taken and the cost actually was larger. So that's kind of the four pieces of information you need to get your t-score. But let's talk about what it's asking. At the 5% level, does the data indicate the average cost of baskets is more than, okay, the mean that was talked about before? So remember, the three things you must list first. State your null. The mean is 145.75. Okay, so that was what it was in July. And then, what's our alternate? What do they kind of ask you to test? That the mean is more than that number. Alright, so now, what's the alpha? 0.05. We need to calculate, now in this instance, we now know it's a sample standard deviation. The standard deviation of a sample, that should instantly trigger t-score. To calculate your t-score is the exact same thing as your z-score. So how do I figure that part out? X bar, what is the average that they kind of talk about? 149.75 minus the mu, which is like your historical number, or once again, it's your null hypothesis every time, over the sample standard deviation this time, $9.50, divided by the square root of how many samples did they take? 35. And that gives you a t-score of 2.49. Now here's where it's tricky, especially when I'm not in class, and I will cover this to make sure we're under the same thing. We need to go to our t-table. Now how this blue chart works is you need to know your degrees of freedom. Now what's degrees of freedom again? N minus 1. Your N is the number of samples, so 35 minus 1 is degrees of freedom 34. Now if you look at your t-table, you're like, uh-oh, I don't have a 34 on here. Well, remember, what do I do? Or that little statement on the bottom of the table says it's the closest degrees of freedom that is smaller. So you're actually going to look at degrees of freedom 30. Now if you look at the very top, the row we looked at in chapter 8 when I did my confidence levels was the bottom row, where it had a C, a confidence level. We are no longer looking at that. We are going to look at, is it a one-tailed area or a two-tailed area? Is it a one-tailed test or a two-tailed test? Since my mu is greater than, okay, if it's less than or if it's greater than, I'm looking just for those particular tails. So in this case, a greater than means I'm just looking for the right tail. So I draw myself a picture. I'm looking for a one-tailed test. So you need to look at the very top row. Now, I don't know how this works. Well, here's what's going to happen. You need to figure out this 2.49 at 34 degrees of freedom. Where does, well, actually I lied, 30 degrees of freedom because that's the next smallest one. Where does 2.49 fall between? Okay? You need to find the two columns that this number would actually physically fall between. And if you go into your table, 2.457 and 2.750 are the two numbers that 2.49 would physically fall in between. Now, what does that help me do? Now you need to go back up to the top of your table, and that's going to give you your p-value. Your p-value is going to fall between, and if you look at the very top row, it's 0.01 and then 0.005 are the numbers right above the two that I've listed down on the bottom. Now, which one's smaller? Actually, is the right one, so this is kind of backwards. So your p-value is going to fall somewhere between 0.005 and 0.01. In this section, or an 8.2, or when you're doing a t-score, you're going to be given an interval. It's not one specific value to compare to your alpha. In this case, it might be 0.008. It might be whatever. It might be 0.01, but all I know is it's going to be falling in between these two. So now I need to compare to 0.05. All right? Now where is 0.05 in conjunction to this interval? 0.05 is to the right of it, which means that this p-value is less than 0.05. What does that mean? If we think back, since it's less than, we can reject. This is significant. All right? There's a small amount of data there. So I can reject my null hypothesis, and then what can I state? At the 5% level, there's sufficient evidence to believe the, now tell me what you're doing, the average cost of a food basket is greater than $145.75. Because that p-value is less than our target value. Okay, it's farther in the tail. There's not much data out there. That means it's very, very significant. Okay, and then you just tell me your interval. So here's another example, just one more to kind of help you look at it, another scenario in case you get stuck doing your homework. Okay, what's your null, alternate, and alpha? I need to list those. So corporations making parts for satellites. There's a gear in that satellite that's designed to be 3 inches in diameter. The quality control officer gets a sample of these gears and calculates them. She had a sample of 95, finds that the average diameter is 2.89, standard deviation is 0.16, tests the claim at the 1% level. There's what I'm looking for, 0.01. That the diameter of the gears is different from 3. So what's my mu? They're claiming that the average is 3 inches. I want to test that it's different from, so it doesn't say anything about less than or greater than, it just wants to be different from 3 inches. It might be less, might be greater than, whatever the case may be. So I need to find a t-value so I can go find a p-value. I know a lot of these letters, but the t-score, using your t-table. What's my x-bar? 2.83 is what this lady found. Your mu is your 3 inches, or your null hypothesis. Standard deviation is 0.76 divided by the square root of n is 95. So if you guys go through and calculate this out, it's negative 1.41. Alright? We need to find a t-score. Now, once again, if you're going to use, or the p-value, the probability, we need to use our table and actually figure out what the p-value is. Now, if you look at your table, there's no negative numbers. That hopefully is kind of a eye-opening thing. Do not be alarmed. It's the absolute value. This is symmetrical both ways, and all this does is go towards the positive numbers on your table. So you can look at this and think about this as 1.41. Okay? Because at one-tailed test, two-tailed test, this table does it for you on the very top. So it's always the absolute value. It'll be the positive number we're looking for. Now, what row do we need to go down to? What's my degrees of freedom? My n is 95, minus 1 is 94. What's the smallest number less than 94? So we actually got to go all the way back down to 80. So if you go to degrees of freedom 80, you need to figure out what two columns does the number 1.41 fall in between. 1.41. So that's going to fall in between 1.292. Let me write this up here. 1.292. And then the next number is 1.453. Okay? So this 1.41 falls in between these two, which then you just need to take those two columns, go up to the top. Now in this case, you have to ask yourself, is this a one-tailed area or a two-tailed area? If I say the mu is different from 3, that's just me saying that I'm looking for the left tail or the right tail. Doesn't matter. I just want it to be different from. I'm not sure which one. So that means it's a two-tailed test. So you need to go up and find the areas or the probabilities of the two-tailed test. So in this case, it's going to end up being, if you actually go to the very top, it'd be 0.200 and this one, and then 0.150 on this one, or 20% and then 15%. Now remember, it's always backwards, so this is kind of frustrating when you do this. But your p-value is going to be 0.15 to 0.20. So this probability of this happening, okay, is anywhere between 15 and 20%. Now is that a small amount? Is that less than? We want it to be very, very small. Rare occasion. So is that rare? No, because we're going to compare that, and that is greater than your magic number of 0.01. So that means we just simply fail to reject. We cannot assume that this is a big significant thing. So fail to reject the null hypothesis. That's the first thing you need to say. Because my p-value is greater than 0.01, it's not very significant. Okay? That means we're going to fail to reject. And just what does that mean? At the 1% level, the 1% level in so there's not enough evidence or insufficient evidence to suggest, and what are we just basically telling you is kind of to suggest that the mean is different from 3 inches. Okay? So basically you're saying we fail to reject, and at that level there's just not enough evidence to say that it is different from, because that was my alternative hypothesis. Okay? So that's kind of your sentence. That's what I'm going to need to see for you to finish your problem. And that's just 2 more examples of it. So once again, just to reiterate, if you reject the null hypothesis, we say the data collected in the hypothesis is significant. It is statistically significant, and then we can say our alternate. If we do not reject, kind of like the very last problem, we say that it is not significant, or we do not have enough evidence to say that it is significant. Okay, so here's the homework assignment that we're going to do. We'll work on them in class. Hopefully you all have a wonderful day.